Thank you very much for coming. It's 11 o'clock, so we'll start with this session. This session is called Understanding the Go Execution Tracer. My name is David. I'm a Go contributor from Sydney. I'm really delighted to be here talking about Go in front of so many people who are using Go in their companies. Like, this is the goal. Like, this is great. So we have 1 hour, 45 minutes, roughly. I think we'll probably talk for 40, 45 minutes, take a little break, come back and talk some more. The other thing, I will try and speak slowly and clearly. Please, if you don't understand me, like I get distracted and talk too fast, just tell me. So this workshop is a collaboration between Francesc and I. We've been going back and forth on the material, like teaching various parts of it for a couple of months now. This presentation, as you saw, is online. It's on GitHub. The slides you can actually run on godoc.org. And please, like, this is open source. The license for this presentation is open source. You're welcome to take and use. Go to user groups, give it at your work, refer to it, copy bits out of it, write a book, whatever. This is yours. The goal is to share the knowledge. As I said, this presentation is about the execution tracer, and we'll learn what the execution tracer is in a second. It was added by Dmitry Vyakov from one of the great gophers from Moscow in Go 1.5. But he, like all great engineers, he wrote the code, landed it in Go, and then it was done. And so you could say that the execution tracer is underdocumented. There isn't a lot of information about how to use it and how to understand the information that it gives you. And you'll see as we go along, it does give you a lot of information. It's not the most intuitive tool. So the goal of this workshop is to help spread knowledge about the execution tracer. As it says there, unlike sample-based profiling, the execution tracer is integrated into your Go program. It's not an external process that is observing your Go program. It's actually part of the runtime. And so the reason this is important is that the tracer doesn't just know what the Go program is doing at any point in time. You can do that with sample-based profiling. It knows why it's doing these things. As I said, we've got an hour and a half, an hour and 3/4. This workshop is aimed at people who have written Go and are using Go in production. It is not an introduction to Go. I just want to make that clear up front. And yeah, there's a rough agenda. We'll see how we go. And the last thing is that, unlike my presentation yesterday, which was just a speech, this is a workshop. This is a chance for us to learn together and to ask questions. So if you don't understand something, if something is not clear, please speak up. I know Russian programmers are very smart and they want to know all the details, so I don't think this will be a problem. I expect a lot of questions. So what is the execution tracer? Why do we need it? I gave a little clue on the previous slide, but I think a good way of explaining what the execution tracer does is to look at the other profiling tools we have in Go and look at the information they can give us and perhaps some of their deficiencies. So the first example is just a simple program that generates a Mandelbrot. Actually, I'll just run it and then we'll talk about it. So when we run it, it takes a few seconds. It's because I'm using tmux, this gets confused. So that's a little bit dark, it's a little bit lighter on my screen, but you run that program, it produces a Mandelbrot of about 512 by 512. The reason we chose a Mandelbrot is that it's a nice computation, a nice amount of computation. Like it's not too fast and it's not too slow. So as you saw, it took some amount of time. Like how do we know how long it took? The simplest way is to use something like time. So this time I ran it, it took about 1.7 seconds to produce the Mandelbrot, and that's for a 1024 by 1024 image, so 1 megabyte of pixels. And just a note, if you're doing any kind of timing like this, don't use go run and time go run, because you'll actually be timing the time to compile and then run the program. So I'll just show you what not to do. So yeah, this has included the 300 milliseconds to build the program. So if you're going to use approaches like time, always so that we're only timing the execution of the program. Okay, so in the example, the program took 1.6, 1.7 seconds to run and generated the Mandelbrot and wrote it out to the file. Is that good? Like, is this the fastest that it can go? Like, is there any more speed that we can extract from this program? And one way to answer that question is to use Go's built-in pprof, which has been available since Go 1.0, to profile the program and try and get a feeling for what it's doing. So, hands, as a show of hands, who's used pprof? Has anyone used pprof? Yeah, okay, that's good, yep. So there are two ways to generate a profile. One is to use the functions in the runtime pprof package directly. And the second one is, the runtime pprof packages are a little bit esoteric. They're a little bit hard to use, and they're inconsistent in their APIs for the different profiles that you want to collect. So a couple of years ago, I wrote just a little wrapper which automates the collection, the creation and the collection of the profile. But for this example, I'll show you both ways, just to show that I'm not promoting this tool as like you must use this. It's just I find it helpful. Good. So to show you that there is no magic here, let's modify the Mandelbrot program to write the CPU profile out to standard out. And this is the easiest and simplest way you can collect a profile. Import runtime pprof, pprof start CPU profile, and you give it an IO writer. Normally it's a file, but just for simplicity, we'll just send it to standard out. And then you have to remember before main closes to call stop CPU profile. Otherwise, the profile that is written is incomplete. So it's important that you have both steps. So I have this example here in the examples directory. And put runtime pprof. So is that color okay, or should I get rid of the color? Can you see? I will get rid of the color. Okay, that's better. So, as I showed on the slide, all we do is we add these 3 lines, and that's going to write the CPU profile out to standard out. Okay, so now we can look at that profile with, actually let me go to the slide where we talk about it. Okay, so we can look at that profile like this. So it's a valid profile. And the important thing, if you're using Go 1.9, yes, Go 1.9, you no longer need to put the name of the binary there. So for, if you're still using Go 1.8, you would need to say it like that. Go tool pprof, the program, and the profile that it was created by. But don't worry too much about that, because when we get to the execution tracer, we don't need that. So that was a really easy way to capture a profile, but there are probably some limitations with this. The first one is if you forget to redirect the output to a file, it's going to crap in your terminal, and your terminal will be all crazy. The second one is that because we're using standard out to be the writer that we're writing the profile to, we can't use printf or anything else. Like any other output, like if we try and use printf, will be interleaved with the profile and corrupted. And so the recommended way to use pprof is to write the trace to a file. But then you have to make sure that when the trace is stopped, that file is closed, and you have to make sure that if someone Control-C's the program, that you properly handle that and close the trace as well. So there's a bunch of like edge cases. And so because of that, I wrote this small package, which is just a wrapper that handles those. And so that previous example in using this package is just defer profile.start, the type of profile we want. So this tool supports CPU, memory, block, and we'll see the execution tracer as well, the trace profile. And you can give it an optional path to where to write it. By default, it just puts it in temp. So it's very similar to the previous example. Just import this package. And you can do it all on one line. You don't need to worry about these comments. They're just for the present tool that tells it which bit of code to show on that previous slide. So they're just comments, they're not important. And so the nice thing about this wrapper is that it gives you a little bit of output. It tells you CPU profiling started, stopped, the name of the file. So you can, it makes it more convenient to work with. So now that we've run the program, collected a trace, let's look at the profile. Okay. So I've covered all this, that's fine. So to look at what's happening in the profile, we can use the top function to say, show me the top functions, the functions that appeared the most in the profile. A little bit smaller. Yeah. And so we can see that most of the time is spent in main.fillPixel, which is so that it's confusing. Like let's be clear here. Most of the time is spent in fillPixel. Some of it is spent in Paint, and there's all this other junk here that we don't know what it means. This is my general complaint about the pprof tool, that it is hard to understand what it's doing. We can make it. We can make the output by saying, please sort it by their cumulative time, which kind of gives a slightly better way to look at what is the most active function. And we can see that main.fillPixel is pretty much using all of the time is spent in fillPixel. And this is not a surprise because this is a 1000 by 24 by 1000 by 24 image, so it's going to call fillPixel a million times to compute each of the pixels in the Mandelbrot. You can also visualize the profile. That's fine. That link's broken, that's fine. And so, looking at this information visually, we can see that, yes, all the time is spent in fillPixel, which calls Paint. So fillPixel computes the complex number for that pixel, and then passes it to Paint to write it, to choose a color and write it into the image. And all of this other stuff here is so small that we just don't need to worry about it. So I wanted to do this example to show you how profiling can be quite limiting. It told us what it saw. It told us that fillPixel was doing all the work. But it didn't give us any clues about how we could speed up our program, how well it was utilizing the machine, or anything like that. And so I think this is a good introduction to the execution tracer, which we'll run on the same program, and it'll give us a different view of what that program's doing. Are there any questions at this point? No? Good? Okay. Don't forget, just put up your hand. So to use the execution tracer, it's as simple as, rather than a CPU profile, ask for a trace profile. If you're using the profile package. The similar runtime functions exist, but we're just going to use the profile package for the rest of these examples, just because that's boilerplate that we don't need to worry about. So that's the only change we need to make, from a CPU profile to a trace profile. Okay, now we'll run the program again. The name of the file that is output is based on the type of profile you asked for. So instead of cpu.pprof, we get a trace.out now. And using the execution tracer it's built into the Go tool. So just as you saw previously, I typed go tool pprof cpu.pprof. We type go tool trace.out. Okay, I'll just quickly show you what it did there. The infrastructure, the visualization for the tracing is built into Chrome, and it uses, I believe, a lot of the mechanisms for the Chrome's internal JavaScript debugging. So what this tool is doing is it loads the trace and is effectively converting it into the format that Chrome expects for JavaScript events. So it just runs a little server and is talking back to that web page. So you need to have this tool running when you're looking at the web page. If you stop this tool running, the web page will stop working. So the index page for this is this lovely specimen here. And the most important one we'll talk about for the moment is view trace. And this is, I'm going to try and make this as big as I can. Okay. So, and this is the screen that we'll be spending the next hour in with examples. And we're going to talk about all the things that you see on here and learn what they mean. Yes, as I mentioned to somebody else, because this is basically using kind of like the Chrome inspector, this tool only works in Chrome. The facilities just don't exist in Safari and IE and things like that to run it. It's just a limitation. I'm sorry about that. So if you're not a Chrome user, unfortunately, you have to download Chrome to use that. And so let's just take a little walk around what we see. On this left-hand side, we have columns like Goroutine, heap, which is the size of the heap. So as I click across here, so we can see for this span, the heap was 4.6 megabytes. So I'm going to say that's in bytes. And then later in the program, there's a kind of a phase change, and you see that the heap starts to grow. We can see it's following that kind of stair-step pattern here. So what's the first thing that you could tell me about this program? Like what's happening in this change from this section to this section? What do you think is happening? Yes?
In the first section, we have a structure map with 2 dimensions to fill in. And later we have something like slice.
Okay. Yep, okay. That's a good. So the answer was, so you're saying in this section we're computing the Mandelbrot, and then we're doing something else.
Like writing PNG?
Yes. Okay. So this is a good time to introduce the controls. It has these strange controls on the right-hand side here, which are part of the JavaScript apparatus. They're not particularly useful. Just try and ignore them. The most useful tip that anyone has ever given me about this is because it's a Google tool, if you press question mark, there's a set of tooltips. Every Google property does this. Gmail, Google Groups, every one of them. If you press question mark anywhere, it'll give you a set of hotkeys. And the most important ones are WS, A, and D. So if you're a gamer, and so W zooms in, S zooms out, and A and D move to the left and right. So let's drive into this bit here, which you said was writing out the PNG. Let me just quickly step out of it. So let's just at any of these spans, we can click on it and we get a stack trace. And you're absolutely right. Yes, it's writing a PNG. So writing the PNG, doing some gzipping of, like PNGs are gzipped internally. So the PNG writer is writing to gzip, which is writing to a file. So if we look at various ones here, you see it's alternating between the PNG and compressing the file. So this is now a good time to talk about Here, proc represents the processors, the CPUs, or more specifically, Go max procs. So by default, Go sets the value of Go max procs to be the number of CPUs you have. This is a hyper-threaded machine, so it has 4 CPUs, so there are 4 procs. If you came to my talk yesterday when I talked about multiplexing Goroutines onto threads, this is exactly it. These Gs are Goroutines, and you can see they're being assigned to different threads. So with that, I want to ask a question. Yeah. So we can see that for most of the program's time, it ran on processor 0, just arbitrarily. And then at some point, it ended up on processor 1 for a while. Does anyone want to guess why that happened? You think about why that would happen? So I'll give you a clue. The PNG, so the PNG goes through gzip compression and it then is written to a file. It's a buffered writer, so eventually that buffer is going to flush out to disk. So, yep. So right here was the point when we did a syscall. This Goroutine went into the write, and we can probably zoom all the way in and probably find that. This is the other amazing thing, that you can just keep zooming in and zooming in and zooming in. I mean, look at the span here. 10 microseconds. Like, you can just keep zooming in and zooming in. And this is a level of detail which is just not available with sample-based profiling. So I was originally going to say that this was because there was a syscall, which meant that one Goroutine was blocked doing that writing, and when it came out of it, it just was picked up by processor 1, just arbitrarily. But looking at this particular graph, I was wrong. Do you want to take a guess at what's actually happened? So the key is to look at this, the heap here. The heap in use, which is the lower color, you can see it's growing up to a point, and then there's a flurry of activity all the way down the graph. What do you think that is? Absolutely. Yeah, and when we zoom in, we can see at this point there was the allocations had overwhelmed the background garbage collector. So it has to, the heap is very small, so this didn't take very long. What we see is because there is some allocation in writing and creating the PNG, eventually there's a garbage collection event that happens. And so all the Goroutines, all the procs are dedicated to running the garbage collector. The world is stopped temporarily, and when the world starts again, we can see that it just happens that runtime.main ended up on a different CPU, because during the full garbage collection phase, all the running Goroutines are stopped, and they're replaced by all the CPUs are dedicated to doing garbage collection. So all the other running Goroutines are stopped, and then when the garbage collection is over and they're started again, it just so happened that processor 1 picked up this Goroutine. So that's why it transitioned between one to the other. Yes?
So this is arbitrarily chosen? I mean, in my case, it doesn't change.
Yeah, it's pretty arbitrary. Yes. But we can look at, there is another. So this was probably the first garbage collection in this program. And in fact, we can probably prove that. Yep, the heap is basically flat before then. So this was probably the first garbage collection event of the program. And now, after that has happened, we see that on the original processor, there is this thing happening. So let's zoom in and look at what that is. And you can just pick any of them. And this is actually the background sweeper. So I don't want to go too deeply into the operation of the garbage collector, but effectively it dedicates some amount of unused CPU, like this CPU is not being used for running a program, to sweeping the heap in the background. And if this background sweeping can keep the heap allocation under control, it doesn't need to do a full garbage collection. So we can see that now the garbage collector has done that. It started a background Go routine to start collecting in the background. Let's just... And you can see that after a while, it just stopped doing even that because there wasn't enough work to do. Can we just look back at the slides? Okay, so let's just look at that image and ask another question. So now, what is this program doing? Is it running as fast as it possibly can? How could we make it faster? Correct. Yes, you can see that even though the main Goroutine doing the computation moves occasionally between CPUs, there's still only one. It's entirely sequential. So yes, absolutely. And I want to highlight this as an example of pprof. The pprof graph told us nothing. Like this just said, paint and fill pixel are doing all the work. It didn't give us any indication how efficient that work was, how well it was spread over CPUs. So this is why I think the execution tracer is a very powerful tool, because it lets you see the operation of your program in real time rather than just kind of observing it from outside. So let's just close that. Okay, so as Sergey figured out, this is just working sequentially. For each row and each column in each row, run fill pixel. And then once the image is painted, the execution switches to that kind of writing behavior, and we see a different phase change in the program. And as you also saw, we get resolution down to the microsecond level. In fact, you can probably zoom in down to the tens of nanosecond level. And this is just something you can't get with external profiling. I think I've gone through most of these do's and don'ts. The first one, obviously, this tool only works in Chrome, unfortunately. Use question mark to get a list of the hotkeys if you can't remember how to navigate around. I don't use the mouse at all with this. I always use the hotkeys. The mouse is, it doesn't behave like there's no clicking and dragging. It just doesn't behave like that. So just get used to the hotkeys. Another one is viewing traces can take a lot of memory. If the size of the trace is directly proportional to the number of Goroutines and the number of events between them. So, and you'll see in the next examples what a big trace and a small trace looks like. Yes, seriously, if you've only got 4 gig on your laptop, you've probably got other problems, but that's just not going to cut it. 8 gig is probably a minimum. If you're debugging some really big traces from production, you probably need access to a machine with more memory than that. And the last one is probably not going to affect most of the people in here because you're either using Macs, but for the Linux people, if you use Go from your distribution like you're using Red Hat or CentOS, they tend to take the support files for the viewer, like the HTML and stuff like that, and put it in an extras package. So if you just install the base Golang package, it may be missing some files, and the trace viewer like just might open to a blank page. So just check out if there is like an extra package, which is usually the MISC contents directory. Yes?
Just two comments. One is that not only Chrome is possible to use, Chromium as well. Open source Chromium, not the only.
Probably, yeah, probably. I don't know a lot about the mechanics of the viewer tool, but yes, it's part of the.
Yes, I have just tried.
Yep.
And another one, well, they're actually not that only graph needs to be installed for this to work. All normal Go package there includes.
Okay, that's good. That's good. When I did a workshop about a year ago in Paris, there were people who were using Fedora who, I was in Amsterdam, and the Fedora package seems to have broken this somehow. Okay, so that's enough housekeeping. So, as you saw from the previous trace, we're only using one CPU, and this program is sequential. But Mandelbrot generation is like embarrassingly parallel. There is no requirement, there is no dependency between one pixel and another, so we can compute them all at the same time if we wanted to. This is embarrassingly parallel. So the Mandelbrot tool supports different modes so we're going to use the same program and just run it in different modes. The mode that we saw previously was sequential. This one, we're going to run a Goroutine for every pixel, and we're just going to say do them all at once. Just time that. So, the time was relatively the same, like thermal scaling on laptops is hard, but you can see that the user time, which in the previous example, let's do that sequentially. So this is just sequential, and this is all the pixels at once. So the real time is roughly the same, like this mode, but you can see that the user time, the number of user cycles has almost increased by 3 times, because we're now using, we now believe we're using all the CPUs at once. Okay, let's look at the trace. Okay, now this is going to be significantly bigger because at a minimum there are 1 million Goroutines and potentially interactions between each of them, which is going to be part of the trace. So you can see the tool is struggling a bit here. When you run it, you can see the difference in the size of the trace file. And the other thing is that when it opens, it will only give you, to limit loading all this data into Chrome, which struggles, rather than being able to view the trace in one whole block, we now have to look at it in little sections. So we'll just pick an arbitrary section. And this is going to take a little bit of time because it is loading an enormous amount of data into Chrome. Are there any questions while we wait for this process? Yes?
Is there any overhead for running tracing tool? Because it should take some resources.
Yes, there is an overhead. I don't have an accurate figure of how much it is. Maybe I would say 10–15%. So in this example, we were starting it at the start of the program and finishing at the end of the program. Later, after the break, we'll talk about turning it off and on when you need it. So because it's built into the Go runtime, there's effectively no cost if you don't use it, and you only pay that performance penalty during the time you're taking the trace. During the break, I can show you the difference in running that program with just that, or you can try it yourself. Just comment out the profile line and look at the difference in runtime. From memory, it was about 1.4 seconds to 1.6 seconds, but not very scientific. Okay, so this is a huge mess. So what we can see here are a whole bunch of things. So starting from the top, the Goroutine line seems to be stable, and then there are huge spikes of Goroutine. So let's zoom into one of those spikes and see what it tells us. So around here, there were 3 runnable, and then in these spikes, we start to see this huge backlog of Goroutines that are runnable, but only 3 running. And the other thing that you should look at from like this overview, it looks kind of like, I mean, there's obviously lots of different Goroutines because you can see the different colors, but it looks like all the CPUs are being utilized. Would you agree with that? Unfortunately, when we zoom in, we see that the actual utilization is very sparse. And what Francesc and I believe is that these gaps here are actually the scheduler. So this represents overhead. It should also be noted that these larger gaps here are actually probably where the trace program is not running. Like it's either like the operating system has scheduled something else there. So there is no trace recorded during this time because technically the program was not running. So you can see occasional gaps in the trace profile if there's another program running on the CPU and your Go program is waiting to run. So that's why we see these larger gaps. But zooming way in here, we see there are huge blocks where no useful work is being done. This is just scheduling overhead. Let me just go back to my notes. And we can zoom all the way in here. And so let's just click on some of these around here. Now, the reason that they are somewhat quantized is that the resolution doesn't quite go this low. So, this one took 320 nanoseconds. This one took 175. Obviously, the clock is somewhere around about 25 nanoseconds, so it can't really record things at a much greater resolution than that. But each of these represents computing 1 pixel. So the amount of work that this is doing relative to the work of playing around in the scheduler to put another Go routine and get it ready, because there are so many runnable at that point, is enormous. Oh, okay, I need to start speaking a little faster. That's okay. Yeah, so what we see here is that running all the pixels at once, we're spending a lot of overhead in just doing the scheduler. So 1 Go routine per pixel is too fine-grained, obviously. There wasn't enough work to justify the cost of that. So let's try a middle ground. Let's do 1 row. So instead of a million Go routines, we're going to start 1,000 Go routines, and each of them will do 1,000 pixels work. So this was much better. We almost halved the runtime compared to the sequential and per row. User time, it's not 4 seconds, possibly because we didn't run for long enough to say 4 seconds of user time elapsed. So this is definitely an improvement. Like doing larger batches of work gives us a significant speed up. So let's look at the trace. Because there were fewer Go routines and fewer events between the traces, we can now see the whole trace in in one file, that's very convenient. It's easier to load. Let me just quickly check my notes. Okay. There we go. Okay. So, who wants to tell me about what they see on this image? Like, tell me about what you interpret from looking at this as how we expected the program to run. We expect the program to do 1,000 Goroutines, which is 1,000 rows. And we can see that at the start there, that we zoom in. The number of Goroutines starts here at 2, which is basically just the background Goroutine and the main, which we can see here. And now as main starts to run, it's creating Goroutines. So it's going around in that loop, saying for each row, start a Goroutine to fill the pixel. Let's have a look at that code. Let's just look at the code. Okay. So the main Goroutine, for each row, we're going to start a Goroutine that does for each column in that row, do fill pixel. I just need to go back to this. And that's exactly what we see. The program main starts, it creates 1,000 Goroutines and then goes to sleep waiting for all of them to be done. And we can see that here. Like now we see all the Goroutines. I'll just get this as well. They're all running nice, orderly work until the end here where we switch to that phase transition of writing out the PNG. We can also see this thread is basically saying, these are 4 procs, 4 threads are all running at this point, and then we move down to that section where we're just writing out the PNG. So let's zoom into the actual main body of this, and things are looking a lot better. Like it's going to, this one per row is going to run for 1,000 times longer than the previous 1 pixel did. So each of these basically represents computing a whole row in a nice big chunk. Like you're doing a significant amount of work. There's not a lot of interaction with the schedule. Like if we zoom all the way in here, we see minute little gaps here between the scheduling, but this is an example of a good trace. Like we have solid Goroutines running all the way across the page. There's not a lot of gaps and overhead. And we see the results in timing. We see we basically doubled the speed of the program. Okay. Yep. So this is just what I said to recap. So we're going to do one more example and then we'll have a break. And we can take questions during the break as well. We support one more mode, which is instead of batching up, like creating 1,000 Goroutines to do 1,000 rows and then waiting for them to trickle down, we can use a mode where we start n workers and then feed work to them. So let's try that. Okay, and this was significantly worse than any of the other runs. I mean, obviously it's using a lot of user time, but the real time was three or four times longer than our best example. So let's look at the trace and try and figure out what this mode was doing wrong. pretty big trace, so it's going to take a little bit of time to load. Oops, okay. So when you have a really big trace, Chrome just pauses on that blank screen for some time, so just be gentle with it. So this is a mess. What are some of the things that people are seeing? What do you see from this trace? This is the span of 250 milliseconds. What does it look like? What does it look like to you that is happening? Zoom in a little bit. What I see is that there seem to be two different Goroutines. I'm just going to zoom in so we can see them. Oh boy, look at this, yeah. So this one, G9, is probably one of the workers. I think this is a channel send and receive event. This is just, I don't know what that is. So another way that we can look at the trace is to go back to this one called Goroutine Analysis, which gives us a breakdown of all the Goroutines by basically the place where they started. So what we see is we have one fill function and one main. So obviously we have one worker in this case. And we can see that. This view lets you just filter out all the other traces just to look at this one Goroutine. So we're going to be looking at the operation of just the worker Goroutine, which is receiving work off a channel, executing it, and indicating that it's done the result. Maybe it's going to load something. Yeah, I have too many of these open. So you can see here that we have the main Goroutine and one worker. So that's the reason why it wasn't any faster. We actually went back to doing sequential processing. Rather than doing each pixel ourselves, we sent it over a channel for somebody else to do it, and then we waited for them to finish that result. Is doing something? No. Okay. So, looking at the trace, sorry, that was a bit of a mess. What's happening is that the producer and the consumer, if we look at the code, are alternating. So. We start n workers, which in this case is 1, and then for every, we pass basically a structure of like the pixel we want it to compute over the channel, and each worker will take a pixel and pass it to fill pixel. In the main Goroutine here, we are looping over the rows and columns and just sending them to the worker. So this is even worse than doing it sequentially ourselves when we just went for row, column, fill pixel, row, column. We're actually sending this value over a channel to the receiver. And there's another problem here. Can anybody spot why? Why can anybody spot a problem with this method of sending work? Yes?
We have unbuffered channel.
Okay, so the answer was we have an unbuffered channel. What does that mean for the interaction between the sender and the receiver?
All the workers will can be blocked by reading from channel.
Yep. It's even more subtle than that. That because this channel is unbuffered, this send cannot happen until this Goroutine is ready to receive. So that means that this producer can never get ahead of the consumer, because if the consumer takes a value and is inside fill pixel computing it, then this is not allowed to send the next value until the consumer comes round to that. So they operate in lockstep. So let's see what happens if we say we want more than one. Let's try and do 4 workers. Let's at least try and try and use 4 workers. And the results are even worse. Like we ran for longer. We obviously are using all the CPUs, but the real time was the worst of all of them. Let's have a look at the trace and see what we see. Yep. We'll take a break in a few minutes. So while that's loading, we have 4 workers, so there are going to be 4 consumers from that channel. So at least at any one time, the producer should be able to communicate at least with one of them, right? Okay, this is really, really interesting. So we obviously, let me just get up the, I don't want that. So we have 4 workers and 1 producer, but looking at the trace, things are really strange. Like there are huge gaps where obviously we can see 1, 2, 3. There are probably 4 colors. There are definitely 4 workers available to consume work, but they don't ever seem to be able to get enough work to do. Like there's not that smooth, filled line of having a lot of work to do. They seem to spend an awful lot of time waiting. And we know it's not the scheduler because the number of Goroutines is low. It's in 4, not thousands. So we know we're not spending a lot of time in the scheduler. But it seems like they're all waiting for something. So my explanation for what's going on here is, as you said, because the channel is unbuffered, you cannot send until someone is ready to receive. Now, the producer can't send work until there is a worker ready to receive it. And the worker can't receive work until there's someone ready to send. So they compete with each other. It's the thundering herd. They're all, they all race to take that one value. And then once that value has been taken, 3 of them lose. And the most important thing is that the sender is not privileged. It, while the workers are off in fill pixel, it can't, it may not be scheduled because they may be consuming all the CPU. So not only can the workers not receive until there's someone ready to send, the sender may not actually be running because it's not on the CPU. So what we see here is lots and lots of latency, those big gaps introduced by the unbuffered channel. Lots of stops and starts inside the scheduler because there are lots of locks that when you go to receive something off a channel, if it's not available, then you lock and go to sleep to wait for the channel to be available. And that's why we see here the sys-time, which is time spent talking to the operating system, which usually represents expensive futex locks and things like that, is really high for this example, and that's kind of borne out by looking at the profile. Okay, so the solution is obviously to use a buffered channel. That means that the producer is not blocked creating work to do, and the workers are not blocked by interlocking with the producer to find that work. So I have that in a different example. So you can see here, rather than the channel being unbuffered, we've given it a size of all the pixels. So that means that the producer never has to block waiting for space. We've chosen to take a little bit of a memory hit. Like this is 2 integers times 1,000,000, so 2 megabytes. But compared to the previous example where we were starting a Goroutine for every pixel, which is about 2 kilobytes per Goroutine, you know, like for a small program, this seems like a reasonable choice. So we'll run it again. This is the same command, but just with a buffered channel. And the results are better. Not quite as good as when we did an entire row in a Goroutine. That was about 7.7 seconds. But it's certainly much better than any other worker example. And let's look at the trace, and then we'll take a break. Okay, good. Okay, this looks a lot better. Let's analyze a few things. Let's look at the heap. So the heap allocated 2 megabytes, which is basically what we thought. It's those two slices, the slices for the positions, and then you can see later in the trace, actually a garbage collection happens, and that memory is freed after this amount of work happens, because that array is no longer referenced. If we zoom in, like, again, we have really nice workers which are not blocked waiting for work. Like, they are just running happily, reading data off the channel. So they are happily, let's look at the code. So each of the workers can happily receive off this channel without blocking, without being stopped waiting for work. So they're happily just chewing through the amount of work they have to do. And we see that in the channel, in the trace. And then here in this final stage, we see that basically all the workers have finished, at the same time. At the same time, so receiving from the channel was not unfair. They all got a fair share of the work, and then we move into this phase of writing out the PNG. We might take a break here. It is 12:05. Shall we come back at 12:15? So a 10-minute break if you want to go to the bathroom, have a drink, whatever. And definitely, if you're in the room, please ask questions as well. This running for less time, like this takes about 150 milliseconds rather than a second and a half. So make the image, we pass it to fill image, which is using the best version that we had so far, which is 4 workers doing a row per pixel, which is the example that we saw. So that's the fastest way of producing Mandelbrot that we know so far. And then when we go to the web service, ta-da, we get the Mandelbrot. It took about 192 milliseconds. So that was the reason why I made this a bit smaller, so that we can do experiments and not quickly overwhelm this laptop. So it unfortunately always serves the same image. I didn't bother to add the features to change the points, but you can see it takes 180, 190 milliseconds to run. So, just to recap what I just said, traces can be very large, even for very small spans of time. So, if you were to always start collecting a trace, and run it for days or weeks or however long your program runs, the amount of data it produced would just be infeasible. So we want a way to connect to a running program and take a trace. And the good news is that net HTTP pprof, who's used the pprof web service? Yep, also supports taking traces. Yes, all you need to do to enable this is just import this, which registers some routes on your default MUX. And now we can, it basically registers this debug pprof endpoint in the router, and we can collect a trace by just curling and saying we want 5 seconds of data. So I'll just run that in the window. So of course this pauses for 5 seconds because it runs the trace for 5 seconds and then sends the trace data back. And you've noticed that the trace is very small. It's empty. Why is it empty? Pardon me?
Nothing happened.
That's right. Nothing happened. I mean, even though, so you saw that. Correct, yeah. I'd called it previously, but during the frame that we were looking at, those 5 seconds, I didn't do there was no work for the server to do. So that's why the trace reports nothing. So the important thing is that you can't collect a trace for something that happened in the past. This is the important thing. Okay, so let's generate some load, because it'll be like flicking back and forth between Chrome and doing refresh. That's too hard. So let's just use something, some load generator. I'm using the tool by Recol called Hey, which is just a web benchmark thing. And the nice thing is that it lets us do 1 request at a second per second. So this just lets me run this in the background, and I can collect a trace at my leisure. So let's just split that. So we can see that Hey is just every second hitting the web service, generating a request. Now we can go back and collect the trace again. So what I'm trying to do is construct a scenario that looks maybe something like what it does in real life. So there's a problem in one of your services in production. You get out curl and you grab a trace for an amount of time. Okay, cool. So does someone want to talk to me about what they see in this image? Like, what does this trace tell them? Yeah, like if you look at the graticule, yeah, it's on the half second. So yeah, this is definitely corresponding to the request. And let's dig into each of the requests. So these are the Goroutines started in response to that request. Just remember there, so this is 193, 192, 190, 191. So if we go across to the next request, these are 167, 169. So it's clear there are different sets of Goroutines related to different requests. They're associated together because these ones were started for this request. They're not workers that have lived previously for other requests. They start, they do some work, they go away, they write the PNG. So this is basically, this is now the trace for that request. You know, we see all of the Goroutines, the workers working on a row at a time, writing back to this, and then it's writing to con.serve, so we're writing the PNG directly back to the browser. We zoom in here, it's the really nice pattern that they're just doing work. Like there's no interaction between each other, no real interaction with the scheduler, so they're just doing work. There's not a lot of overhead. And what I want to now introduce to you is the network column here, which is really small to hit on. So can everyone see there's this tiny little event here? And this represents the packet being received by the networking subsystem and being dispatched to this Goroutine, which is, so the traditional model is you call accept, and then you create a new Goroutine to handle that connection that was just accepted. Zoom in a bit more. Now, so the next feature I want to introduce to you is some more of the details here. The incoming flow, we can say, why did this Goroutine start? What caused it to be runnable? And if we click on this one, we can see that there is now an arrow between the network event and this Goroutine. So this Goroutine started running or woke up because of a network event. Let's have a look at the outgoing flow. Oh, that one's not particularly. Okay, so we can see here that this is the spawning of the workers that we started. There is a line, outgoing flow. So the words unblock mean channel event. The word go means started a go routine, like the go statement. So we can see that this go routine here spawned these other workers here. If you hover over that, you'll see arrows pointing to that. So now we know, now we can trace why did a go routine wake up and why was a go routine created. We can find that out we can do this here, do the same thing. So you find a go routine. Incoming flow means I was started by the go statement, and you can see this go routine was started by that one there. So This is super useful. Doing on time. Okay, good. Are there any questions? Because there's one more example I want to show. If there are no questions, I'll move on to that. Okay. The next part of this is basically increasing the rate at which we. So now we're doing 5 connections, 5 requests per second, and you can see that the time has shot up here because, okay, actually, I'll ask that question. Why has the time shot up? Like, why has increasing the request rate caused the time to handle the response to go?
Because requests are handled simultaneously.
We have the same amount of processor, but more job.
Okay. Yeah. No. These are all the same answer. There is more work to do than can be processed by the machine. During this request, which is 180 milliseconds, the entire machine is occupied doing this. Now, at 1 request per second, they don't overlap. Like, we know that these are independent groups of Goroutines serving a particular request, but they don't overlap. So they don't interfere with each other in terms of slowing each other down. Let's look at the trace now when we're running 5 requests per second. Grab another trace. Watch here very quickly. There will be, yes, so you can even see the request to the debug handle. I just put a logger around the whole HTTP router, so every request, including the ones to the debug endpoints, get logged out there. Okay, let's look at the trace. Still pretty reasonable, it's only 5 seconds. So now if we I'm going to go to, this is roughly 1 second. So during this time, 5 requests have come in, and we can probably trace each of those by looking at the network events, which are either sends and receives on the network, to Goroutines being spawned. So we can trace the network event to the handler to creating the Goroutines for to service the request. Now, your answer was that they're overlapping, did you say? Does this trace kind of suggest that to you? Yeah, they're all kind of intermingled. Like, all the Goroutines, there was some created for the request, and during the time that they were running, more requests came in. So more Goroutines were created, just kind of added to this pool. And even though this is a synthetic example, I think it also represents much more the kind of trace you're going to get from a real-world server. We have an unbalanced mix of requests doing a bunch of things. Now that we know that writing out the PNG creates a lot of garbage, and so as we're writing 5 PNGs a second, there is now interaction with the garbage collector. So I'm just going to point out a few other things on this, which we haven't seen before. So the first thing is this activity below the line. This activity above, kind of here, represents the code that you wrote. This area below is usually representing work that the runtime is doing. Let's zoom in and have a look at what it's doing. Just going to find some. So these are sweeping and back. Let me just make that bigger. Sweeping and background Goroutine activity. And so even though the stack frame of this is the serve method, there's probably a few more stack frames in there. When we look a bit closer, we see that in writing out the compressed image, there has been some allocation taken, and because of the pressure on the garbage collector, it is decided that this Goroutine needs to do a little bit of work to pay for the allocation it made. So I spoke previously that the garbage collector starts with background Goroutines for free CPUs. Then as the heap pressure increases, it starts to make, when you make an allocation, you have to actually do some work to clean up some allocation before that. And that basically continues until a full garbage collection, which is you make no progress and you are dedicated to cleaning up the heap. So what we can see here is just normal background garbage collector pressure, and we can see this in the kind of stair-step behavior of the heap. Right? It comes up to that peak and then drops, comes at the peak, drops. You can trace those yourself to look at the garbage collector events that happen at that time. You can see that the kind of number of Goroutines fluctuates up and down as we have requests in progress and new requests coming in. So let's just look at that. So, we have 17 runnable Goroutines and 4 running. So there are 4 on CPU and 17 in the queue. So it looks here, it looks like the number of runnable is going down, and based on what we know about this program, we know that after you generate the Mandelbrot, you move into a single-threaded phase of writing out the image. So obviously, one of those requests has moved from building the Mandelbrot to writing it out, and so that's why the number of runnable Goroutines goes down. Okay. Yes, in the interest of time, I'll move on to the overload. Okay, in the interest of time, I'll move on to the last example, which is has everyone seen the prime sieve example from Go? This is the Sieve of Eratosthenes. Oh, damn it. Which produces primes by a process of elimination. If we pass a number down a channel of a connected channel of Goroutines, each of them is responsible for one number. It says if this number is a prime, then print it out. Otherwise, pass it on. This example, am I online? Yeah, this example, Ivan Daniluk had a great presentation at GopherCon where he visualized the concurrent prime sieve. And we can see here that 7 is a prime, so it's returned. The next number around, obviously we're only counting odd numbers. 13 is passed around, and then 13 is prime. But you see this behavior that as the numbers increase, the number of steps around here increase. Now let's look at this in the trace viewer. Okay, there's obviously a lot of work doing, but I want to use this to illustrate another form on this, which is the Goroutine analysis. So if we look at the main Goroutine, this filters out activities which are unrelated to the main Goroutine. So we can just focus on, in the previous example, when we were serving the web requests, if we could find the Goroutine that was the one that accepted the connection and spawned off the work, we could filter out all the other background activity. But in this one, we have runtime.main, which runs the whole length of just producing numbers and running the generator and fitting them into the channel. And if we turn on flow events, which is basically those arrows that we're hovering over, we just say to turn them on all now, we can see a structure which is very similar to Ivan's. In Ivan's, the blue lines represent goroutines, and the arrows around the outside are communications between those goroutines. I might just run this again. It wasn't the prettiest. Sometimes it's not that pretty. Yeah, that's better. So we can see the behavior here. Filter, 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 and when it actually finds a prime, it passes the prime back to the main goroutine. And as we move on through higher and higher numbers, we see that the chain of filters gets longer. Like you're passing to 1, it says, well, 1's on a prime. Pass to 2, it says 2. And this very closely matches we see here. Like, for example, the 15 is just discarded, it's not a prime. And only the numbers that are passed back into the central goroutine are the ones that are printed. So, say around about 7 is the 4th or 5th prime. Yeah, I'd say that would probably be the one for 7. There is a bunch of steps, and then the number 7 is returned back to the runtime over a, let's look at, over a channel. So that's the number being returned to the main goroutine for printing out. This is all the time I have, but we can talk about this for the rest of the day. There is lunch straight after this. I hope that in the conclusion I said, now you know everything about the execution tracer. You certainly know everything that I know about the execution tracer. It's a very powerful tool. The interface is not the best, but it is certainly, you can use it, and people are getting really good results with it. There's a number of videos which you might be interested in watching. The top 2 are by Reese Hiltner, who works for Twitch, who has done a number of presentations on how they debugged production problems with the trace tool. The next 2 are not directly related to the trace tool, but are more generalized. This is my 7 different ways of profiling Go programs that I gave last year, and the materials from my performance workshop, which maybe some of you who were in Paris last year saw, and a video of Ivan Daniluk's presentation about concurrency in Go. So thank you very much for your time. At the back, do we have to leave straight away, or can we take questions, or? Okay, so we have 10 minutes for questions. Yes?
I have a question. We used only one channel to send data from producer to workers. But what if we have many producers and many workers? If just one channel is off for us, or we should have several channels?
In which example? In the Mandelbrot example?
Any example?
Okay. Okay. So you're saying, what if we had a channel per worker? No? No.
I mean, just one channel. Is it bottleneck for large amount of data which we will pass through channel from producers to workers?
Is it okay to use that, or should I'm not quite sure of the question.
I think he meant that should we use...
I'm asking about capacity of channel.
Okay. This example is quite unusual. That we choose to make, like this was the original example. We choose to make. We choose to make the size of the channel the size of the image. So this is done in this way to ensure that the producer is never blocked. It is unusual to have that. What is much more usable in worker scenarios is that the reason that this is problematic is that the work, like doing one pixel, the amount of effort to send that work and for somebody else to receive it is much less than the amount of effort to actually do the work. Let me show you the example from the exercise. Which this is, rather than sending each pixel, we send the number of the row, and then we do each pixel inside that. So the size of the channel there is much smaller. It's now only each row. What we saw during the break, we did an example where we made the channel smaller than the amount of work to do. So the producer could produce some and then would have to negotiate for space as it came. And what we found is that once the producer had filled up all its space, it slowed down significantly because it had to go into that mode of negotiating. So the size of the buffer of the channel really depends on what work needs to be done. In this case, because this is a heavily computation involved, like this takes a lot of processing power, which competes with the producer. It's best to make sure to allocate all that memory and make sure that the channel can be as big as it needs to be. If you had different workloads, like this was a HTTP request or like a WebSocket or something like that, where most of the time spent doing this would be, the Goroutine would be blocked, talking to a database, talking to a WebSocket, talking to Kafka, whatever. Then you may have no buffer at all. Like it's much more common to see channel sizes of unbuffered or just with a buffer of 1, so that the producer can send and then continue on its way rather than being blocked waiting for that intersection. So this is an unusual example that we chose to make the buffer so large. Normally the buffer is 0 or 1. Hopefully that's a useful answer. Another question? No? Then yes. Okay, I'll get you next.
Thank you for the talk.
You're welcome.
So if we have Goroutine, which is trying to send data to the channel, which is blocked, and blocking on it, does scheduler doing some optimization regarding this, or like it's just blocking and the scheduler does not know about it, and it's still running on the processor and being occupied?
Okay, the best and shortest answer I can give to that is a talk by Kavya Joshi at GopherCon this year, where she talks all about channel sends and receives and the operations that happen in both blocking and non-blocking mode. So I won't answer. I'll link you to the video, which she did a much better job. In fact, I'll just put it in the slides. Yeah. The super short answer is there are fast paths if there is capacity in the buffer. Nobody goes to sleep, nobody blocks. But if the buffer is full, then the sender is the sender is recorded so that when somebody else comes back to receive, they are instantly put back together. Very similar to the way that if you came to my talk about networking yesterday, the scheduler knows this Goroutine is waiting on this network packet, and so as soon as the packet arrives, it puts them together. But I'll put Kavya's in. I'll attach her to here, and you can watch it there. You had a question, yes?
some branch with error.
You should definitely look at Reese's talk from .go 2016, where he had exactly that. What I believe that they did is they collected hours and hours worth of traces, and they looked through them. It is not the trace profiler is not a debugger. You can't put conditional breakpoints and things like that. That I don't know if that's a feature that could be added, but it's certainly not something that it does now. Its unit of the unit that it works with is not stack frames and branches. It's actually the interactions between Goroutines. It records an event when Goroutines talk to each other. It's actually recording these lines not so much as the sections within them. But I think Reese's talk is probably the best one for that. So watch the first link on that page. And was there another question? Yes.
Thank you for your talk.
Thank you.
I also like to ask what were trace file sizes when the trace tool starts to
Let's take a look.
feel that it needs to split.
Let's take a look. Yep. Okay, so let's do the sequential trace. And the per pixel one. Okay, so sequential and the per process one. Like this is 44 kilobytes. This is 18 megabytes. And the major contributors to that size are the number of Goroutines and their interactions. So it's effectively a representation of the number of lines, the number of interactions between them. But in terms of when it broke it down by like 200 millisecond, how does it decide to do that? I don't know the exact number of like 5 megabytes per screen or something like that. I could certainly find that out. I suspect it would be 2 or 3 megabytes per screen.
And you have one more question. Is the trace tool able to lose any information about runtime? So is it able to skip anything?
Do you mean filter out, or are there things that it can't measure?
I mean that can I rely on completeness of this information?
Yes, so far as I know, it is not incomplete. The places where you will see gaps that we saw on the previous profile, when the program itself is not running, as in it's not on the CPU, the operating system has given that time to something else, you may see gaps. And the thing is that there'll be gaps all the way down because the whole, most likely the whole program is off the CPU. An example of that, when Francesc did this talk, he was running Screen Recorder in the background, which is quite computationally expensive, and we saw quite large sections where obviously his Mac was doing something else.
But is it related to only the trace process or the whole program where the trace is...
Literally, the program is not running at that time. The operating system's given that time to something else, like the network card or Chrome or YouTube. The gaps are not missing information. They are literally time. That is time when the program is not actually running on the CPU. So we have Goroutines which are being scheduled onto threads, but if the operating system is really busy, then those threads may not actually be running at all, in which case there won't be information there because the program was not running. The information is not lost, in that it was not recorded, is literally the program was not running, so there was nothing to record.
You can just see only gaps in, but they are not losses of information. Yeah?
Correct. There was nothing to record during that time because the CPU was servicing another program. When I'd see that, I would say that is an indication that the machine is overloaded, it's overcommitted because your program is not running. Somebody else's program is running during those times. This will be the last question, but we can talk at lunch.
It's related to the same
Yep.
question, but the tracer keeps track of everything which is happening in the program, right?
Yes, it keeps track of everything that's happening in the program because unlike sample-based profiling, which is looking in from the outside, these events are emitted in the call paths of the scheduler. There is literally lines that say, record sched trace, record this particular trace event. They happen as part of the program execution. It's these, the mechanisms that record this information are in code inside the runtime. And when you turn the trace on, rather than just throwing that information away, they add it to the buffer to be written out. So it's not possible for the trace, for information to be missing from the trace because some external party was not watching at the right time. This information is written out as part of the operation of the program. That sounds like a good place to leave it. Thank you so much for having me today.